All right. Good morning. Well, welcome to the session on reactive programming, creating highly responsive applications. My name is Venkat Subramaniam. We're going to talk about reactive programming, but in addition to talking about it, I want to develop some examples so we can get a feel for what it really is about. Best time to ask questions or make comments is when you have it, so please don't wait till the end. Anytime is a great time for questions, comments, just about anything. And if you do have a question or a comment, I request you to draw my attention because these two lights are completely blinding me. So if you raise your hands, I won't be able to see you, and I'm not trying to ignore you at all. So ask questions, make some noise, draw my attention. I'll be more than happy to listen to you. Would be delighted to have your discussion. So let's get started. Let's talk about reactive programming. Well, the very first thing I want to say about reactive programming is, I think when they named it reactive programming, they did not think of one thing. I live in the US, and in the US there is a negative connotation to the word reactive. You don't go to somebody and say you're a reactive person. You just lost a friend if you did that. So the word reactive is usually considered to be a bit negative, but the true sense of the word reactive simply means that something or somebody that is very good at responding to change of activities, change of events, stimuli that's happening. So in the true sense of the word reactive, it means exactly what it is. But I think they could have been better named as proactive programming. That would have been, we'd have had double the number of people interested in the talk in that case, I think. So anyways, but reactive programming is gaining quite a bit of attention recently and seems to be like an exciting time. But I want to start by asking the question, is this something totally new? Well, there's one thing I've learned over the past few decades in this industry. We live in a field where every 10 years we'll give a new name for what we already have and get excited about it. And this time around, it seems to be reactive programming, and we are excited about something that's been around for quite a while. So no, this is not anything new at all. In fact, in a way, I would say reactive programming is kind of like extreme programming in a very different level. If you think about extreme programming in the process world or in how we execute projects, extreme programming didn't have anything new at all, and yet it had something really new, and that was a greater emphasis on a certain software practices. Like, for example, doing pair programming and doing refactoring and active design and stuff like that. In a similar way, reactive programming at the application development level is focusing on certain practices that has been around for quite a while, so there's nothing new in that regard, but it brings it with a greater emphasis. So in other words, it is really old concerns, but they've been brought with a renewed urgency and greater emphasis and interest. But the question really is, what changed? Why should we have this renewed interest? Why should we really care about this? Well, if you really think about it, the world around us has changed quite a bit. I'm almost nostalgic when I say this, but I remember, and I could actually hear this in the back of my head, the days when I would wake up in the morning and I would turn on my coffee pot, and while the coffee pot is brewing, I would turn on my modem. I could hear the whoosh sound of the modem, and it would take several attempts to connect. And when the modem connects, I would call my friends and ask them, what's your baud rate today? Well, those were wonderful days. I don't know how many people in this room remember the modem days. I mean, I got children these days, and I say, oh, wow, show of hands, that's great. Absolutely. So I didn't see how few there were, though, which is kind of shocking, right? And I have children, and if I say the word modem, and they kind of look at me, it's like, what's that? And so it's an embarrassment to say about these old technologies these days. But anyways, but things have changed today. We carry multiple devices with us, each one of us do, and we have information at our fingertip. If I'm in a car, for example, and we're driving along the freeway, and I say something, or somebody in the car says something, and somebody says, what does that word mean? And before the next person could respond what the word means, the kids have already looked it up, and they are having the definition on their hand. So we are in a world where information is available at our fingertips, which means we are dealing with very different kinds of applications that we are developing. For example, we are dealing with the world of big data. Not just big data, but I would like to call it as freak frequent data, where we have a very high volume of data interaction and data access that's going on. Now we are dealing with internet-enabled devices. I don't carry anything with me. I don't really like to wear a watch. However, my son is the biggest geek in my family, and he's got almost every device that's in the market. He actually goes and works part-time, and he's only about 16 as of today, and he's got a part-time job only so he can go buy devices. He's got wearable devices already, and that's kind of the trend today, is that people are going to have various different devices. People walk with multiple devices. People wear, nose rings, earrings, tongue rings, what have you. And all of those are internet-enabled these days. And it's amazing how that world is going to change as we move forward. And as a result, the usage pattern is very different, where people are going to be using these devices, and these devices constantly are communicating with internet-backed device applications. And as a result, we need to be serving these applications very, very quickly. So in other words, we live in a very different usage pattern and devices and applications today than we used to run in the past. In the past, about 20 years ago, and if you consider some of the US banks even today, they run millions and millions of processes in the night, but it doesn't really make sense to be doing that anymore. With all these different applications being internet-enabled and available, we almost are dealing with constant flux of interactivity. So in other words, what we want is reactive applications. Well, what in the world then is a reactive application? Well, it is really a rehashed programming model. Like I said, it really doesn't have anything new in it. It is something that has been around for quite a while. We've been excited about this for a while, and we've been really working on it. But except that we've been working on it piecewise, and we've been doing it a little bit here and a little bit there, this brings together a greater visibility into the problem and a greater emphasis on certain solutions. And it emphasizes on two, at least, very important things. One is scalability and the other is responsiveness. But that's not it. It also emphasizes a few more things. We'll talk about it in just a minute. So it is a programming model that is really geared towards very high scalability and very fast response for applications. Now, we could talk about why these things are important, but a lot of those are kind of obvious. But it's important to kind of revisit so we are on the same page. It's really a way to build a very highly scalable architecture that is resilient and also very quick to react. So what does that really mean? Well, scalability simply means that we can address and provide access to a large volume of interaction. So we want to be able to provide a very high scale, and that means we don't really want to contain it to batch processing. We don't want to contain it to a small number of users. We want to be able to provide access based on a world full of users as the demand may increase. Now, clearly, not all applications are going to require this. However, quite a substantial number of applications are requiring it. As an example, I've driven through toll roads for a very long time. And in a way, sometimes I don't want to go through, used to be that I don't want to go through toll roads because in peak hours, the toll roads could block up so much that you would have to stop to pay toll. And depending on the city where you lived in, the traffic would pile up for 4 or 5 miles sometimes just to go through the toll road. And it was much faster to just go through the roads sometimes. But today, in almost every city I travel, the toll roads are totally unmanned. You have automated devices that are constantly monitoring the traffic that's flowing through, and the bill is almost instantaneous. And as a result, we are looking at millions and millions of cars that go through busy city roads, and tolls happening at the same time, being paid through these services. You can look at several examples like this where we are looking at internet really promoting a greater degree of interaction and responsiveness. As a result, scalability becomes extremely important. And resilience is very important too, because if you really think about applications, we don't want applications to be broken so easily, because if applications are broken, that's the easiest way to lose customers, because nobody wants to use a broken app. They really want applications that actually work. And so resilience is extremely important as well that we want to provide. So what is really a reactive application? Well, the very first thing is, it is message-driven. Now let's think about message-driven just for a few minutes to understand what does it really mean. Well, there's something that's been exciting and happening for a good many number of years, but more so, I would argue, within the past about 5 or 6 years. Again, this is not new, but it has taken a really good, greater interest. If you think about multi-threading, in Java, especially in the JDK, we are dealing with threads. You create a thread, and then once you create a thread, you are saying, I'm going to delegate this particular task to this other thread. But the problem with threads is enormous. We have to make sure that the threads don't run into each other. We have to synchronize it. Now, when you have to synchronize the thread, how do you manage synchronizing the thread? Well, if you synchronize the thread, you have to make sure that you have synchronized the thread at the right place. You have to make sure that the synchronization happens for the right duration. You have to make sure that the synchronization is happening at the right place. And these are so many places where we could go wrong. So here's a question for you. If you forget to synchronize, the Java compiler gives you an error, correct? No, it doesn't. Okay, it gives you a warning. What do you think? No, what does it do if you don't synchronize properly? It doesn't do anything. Actually, it does something. It calls the other compilers, and they all laugh at us during the night, right? They say, these guys thought they could write code, concurrent code, using JDK like this, right? Well, it's really complex. And in fact, before I read Brian Getz's book, the Java Concurrency and Practice book, people told me, you can never get concurrency right if you haven't read Brian Getz's book. So I read the book. And after reading the book, I realized I would never get concurrency right. And the point is, it's so darn complex that no human being can ever get this right. Okay, maybe no human being other than Brian Getz can get this right. Well, the problem is this, right? It's extremely difficult to get concurrency right. Well, you could invite people like Brian Getz and say, could you please fix it? And they would go through the code and they would get the concurrency right. But before they leave, they will say one thing out of the door, and they will say, I fixed all your mess, but don't touch the code anymore, right? Because every time you touch the code, potentially concurrency is going to be broken. Well, the point is this. Why are we trying to solve the problem in the most difficult way? Einstein said that doing the same thing over and over and expecting a different result is the definition of insanity. Collectively, as an industry, we are insane when it comes to the way we have been solving concurrency. Well, thankfully, there are certain solutions available. This has been around for a long time, like I said. Erlang brought about the so-called actor-based concurrency model. Well, Erlang systems are often credited to be one of the most reliable systems out there. If you go out and look for Erlang, they are talking about mean time of failure being 0.000, keep putting several zeros and a 1 milliseconds every 6 months or so. So very reliable system built using actor-based concurrency. Well, thankfully, this actor-based concurrency model has been brewing for quite a while. Now, if you really think about it, what is the real problem with concurrency? The problem with concurrency is that we have been doing object-oriented programming really bad over the past, a decade or so. When object-oriented programming was created, the intention was not to really pollute state into objects and have multiple threads go at it. Alan Kay, the guy who termed object-oriented programming, even though it was created by 2 Norwegians, he said, when I created the term object-oriented, I quite did not have C++ in my mind. And Java follows suit in that regard in terms of how we do object-oriented programming in these languages. So the point really is, when we have objects, what happens? Well, mutability, we take objects in mutated state. Well, is mutability really a bad thing? Well, most people would say, well, it's really not that bad. We've been doing it for 20 years. How could it be so wrong? So mutability is okay. What about sharing? Well, sharing is a good thing. Remember what mom told us. Sharing is good. But shared mutability is devil's work. And the minute we bring shared mutability, all kinds of things mess up. So that's the world we lived in here in the case of programming with OO in Java and most of the other object-oriented languages. The other extreme, way over there, is these guys programming in the so-called functional programming languages. And those guys sit there and they tell you, we write code and nothing ever changes in this code. And you look at this and say, how could you possibly write a code where nothing changes? And for most of us, this seems to be something so vague and hard really for us to achieve. Well, thankfully, there is a balance I'm hoping we can strike in there. And that balance I would like to call as isolated mutability, if I know how to type this morning. So isolated mutability. And what is isolated mutability? Well, isolated mutability is we have a mutable state. However, we do not modify this state from multiple threads. In other words, an isolated mutable state is where no two threads will modify this particular state at a given time. At most, one thread could possibly be modifying this particular state. Well, actor-based concurrency really is isolated mutability, because it says this variable is mutable, but no two threads can ever get to this particular mutable state at the same time. So it guarantees that there is thread safety in this particular mutable state, because multiple threads can never run into each other modifying this mutable state at any given time. As a result, we don't have to focus our time and effort writing and managing synchronization. Instead, we can focus our effort in message passing, and as a result, we can focus on developing application and not attacking the accidental complexity that often brews from synchronization and concurrency management that we often get into. So the nice thing about this is we can use message-driven systems to eliminate the problem of concurrency. So that is one of the first things in reactive programming, is that we build applications using message-driven solutions. We don't get into the mess that we deal with in the terms of concurrency, and instead we are going to deal with separate isolated threads that can run on different machines, if you will, or different processes, and we can communicate between them using these messages. That is one of the things about reactive systems. The second thing about reactive systems is elasticity. Now, what is elasticity? Well, throughput and scalability is extremely important to us. However, how do we really make things much more efficient? Well, we could be throwing a lot more thread at our process. But we all know one thing: the number of threads we can have in an application server is largely limited by the amount of memory that this application can have at runtime. And no matter how hard we try, the number of threads is fairly limited. So if we're going to use threads to really scale, that is a limitation already. Well, one way to solve that problem is to put a cluster of machines to solve it. But the problem with clustering is often clustering can end up being a very static solution. And when we have a static solution for clustering, it becomes very expensive to manage this. The problem with a lot of different applications is we don't know what the demand of these applications are at a given time. There could be a high demand during the certain part of the day. There could be a low demand during other parts of the day. I've got a client, for example, where their application is fairly widely used by thousands and thousands of users during any given day, but on the first of the month, between a certain hour, their usage would just explode. And because something in their business happens on the first of the month, and almost every single customer they have is interested in using their application, so there would be a fairly good demand on their application, and there's a burst of usage for several hours on the first of the month, only to come down, and it would stay very reasonably, relatively low to, so to say, rest of the month. Well, how do you manage a situation like this? You could say, I'm going to take the peak load and provide a service based on that. And in that case, it means 29 to 30 days in a month, your servers are idle, consuming resource and money and everything else. And on the other hand, on one day, everything gets used. On the contrary, it may be possible that on that one day it's not able to serve either, and then now you're worried about how you're going to keep up with the demand. Well, this is where the elasticity really comes in play. And again, the world has seen quite a number of solutions with the cloud computing and the ability to deploy machines at will. When the demand increases, either you project the demand increase at a certain time of the day or certain time of the month, or as the demand actually increases and the servers are getting busy, dynamically servers can start up, fill in the gap, they can start processing the requests, and then when they are done, the servers can start turning off, and as a result, you can be very cost effective in terms of how you dynamically grow and shrink your services, and we know that is elasticity. And again, reactive programming says, let's worry about what we need to worry about, which is application development and getting the revenue out of it and serving the customer's need. Let's not worry about the infrastructure, because there are technologies like Elastic services that take care of that for you, so let's rely on that. So once again, notice that that's not new, but it really brings these two into one fold to say, we will want to think about concurrency, we will want to think about scalability, but let's think about it together using these different technologies. And resilience. Now here is one of the problems, right? Most of us writing code, what do? We write the happy path in the beginning. We make sure everything is actually working. And then eventually, we come back to handle errors after that. And when you do error handling in the end or after the fact, we don't do a good job error handling. And oftentimes when systems fail, they don't fail because everything went right. They fail because something really went miserably wrong. And so error handling becomes extremely important. This is a design decision we have to be careful about as well, because we don't think about error handling and how we're going to be dealing with problems and failures. We may come after the fact, and our design may not be able to accommodate properly these error handling. So resilience is something extremely important. This reminds me of something I heard recently. I've been teaching part-time at the university for about a few decades now, and a student came to me, actually somebody in the industry came to me and said, hey, I took your class about 15 years ago. And I said, oh, that's really awesome to meet somebody from the past. And he said, I want to share an experience with you. I said, okay, well, I'm ready to listen. What do you have to say? He said, well, I took a course from you. It was called Distributed Computing. This was way back in time. And I took this course, and we were doing a demo on the final day, and we were demoing this project. We were all really proud about showing what he had developed in this distributed computing application. And while we were in the middle of the demo, all you did was you quietly walked up to my machine, unplugged the internet connection, and went back, sat down quietly and said, please continue. And we all failed that course. I said, I'm really sorry to hear this. He said, no, this has been a great experience ever since, because that failure taught me I should think of failure to begin with. And every time I write code, your evil figure comes in my mind, and I think about you, and I've written better code since then because I always handle error first now. Well, that was a very wrong way to teach, in my opinion, but I nevertheless did. And the point really is that it is important for us to think about error handling from the get-go. That's extremely important, and we cannot just come back and think about it at a later time. So resilience is extremely important. And responsiveness is also very, very important. Now, if you really think about it, why do we normally go for multi-threaded applications? It is not always to get better performance. It's often really for getting a better responsiveness. Now, why is responsiveness so important? Now, let's think about this for a minute. If you walk into a store, and as soon as you walk into the store, it's a very quiet Sunday afternoon, so it's not a very busy time. It's a fairly an empty store maybe, and you walk into the store and you realize that the clerk is busy helping somebody else, and you probably stand around, look at the ceiling for a few minutes, look at the floor for a few minutes, look at the wall, look at the shelf, and then what do? You probably quietly leave. Why? Because you feel that there was not any response at all. On the other hand, you walk into the store, and as soon as you walk in the store, the clerk who is busy helping somebody makes an eye contact and says, hey, thanks for coming, we'll be with you shortly, chances are you waited for 15 minutes in the store. Why? Because you felt you were important, even though you know very well you are not. So the point really is that you are really responding to the fact that they were responsive. Well, the same thing applies to the applications as well. If you visit a site and the site is spinning, you are thinking, is the site really taking time to respond, or is it that something is broken? It's even worse, right? If you're going to a site and the site is not responding quickly, it's spinning, what do most users do? They hit the refresh button. So this only makes the problem even worse. Now you got 2 threads doing the work instead of 1, and they click a few more times. Now you really brought down the site because there's more threads you are using on the server. So now we are part of the problem than being part of the solution, right? And of course, it doesn't help to really respond back saying, our site is busy, please visit later, because that only prompts users to click again, refresh button to see if they can get through. So there is really no way to fix that. So responsiveness is extremely important. And when an application is responsive, that is going to keep more users using our application than when we have applications that are pretty unresponsive. So that is something for us to keep in mind, and ability to really provide these things. So in short, a reactive application is an application that is built with these 4 pillars in mind. We want to be able to provide scalability, but we do that by creating applications using message-driven architecture, by using elastic computing, by providing resilience from the get-go, and to provide responsiveness in applications. Well, but to really provide scalability and responsiveness, can't we simply use multiple threads? Now, I already talked about some of the problems with multiple threading, but that's only the beginning of the problem. Let's say you are creating multiple threads, and while multiple threads are running, let's say one of the threads ends up failing. How do you get notified when one of those threads actually failed, and how do you really respond to it? Well, most of the time, you don't get an exception when a thread fails. You're not notified properly about it. And even if you did, what if you have started 1,000 threads in your thread pool and number of threads, 79 of them failed? How do you get all these messages, and how are you going to handle some of these problems? And while you're trying to handle these problems, what are the other threads doing? They're all continuing, and hopefully they are passing, but some of them may start to begin to fail as well. And this is worse than trying to manage a kindergarten, right? Where there are crying babies and you're trying to say, please quiet, and the other babies start crying, hearing this other baby to cry. Multi-threading is kind of like that when it comes to error handling. It just gets out of control very quickly. Now, of course, we all know exactly how to solve it. We reboot the server and the problem goes away for a day or 2, right? So this is not the way to really handle the solutions most of the time. It's very frustrating. And so multi-threading doesn't really help us. Hey, what about futures? Aren't those cool? You could call a future and the future can give you an error back or a response back. Isn't that really cool? But honestly, let's think about how we wrote future, code with future. You call a thread, it gave you a future. What did you do right away? Turn around and call get on the future. That's no future at all, right? So as a result, that doesn't really help us to make better usage of our resources. It's a very low level of abstraction, but it's very difficult to compose with it as well. But like I said, it really is a very poor utilization. With the futures itself, if your future is going to get back a collection of objects and then you have to navigate even further with it, then you are really looking at a nested structure. It really becomes hard as well. So those are some of the problems with futures. But we got other solutions we have tried before. Can't we just use callback? If you think callback is a good idea, I've got a suggestion for you. Go to a good friend that you have who is a good expert in JavaScript and just say the word callback and watch them begin to cry uncontrollably, right? And that is how callbacks are, right? They can really even take the unshakable person and make them really weep. And that is callbacks, right? Callbacks are miserable. They don't compose very well. They really are hard to work with, a very low level of abstraction again. Okay, so we looked at some really hard to use technologies we have worked in the past, but how can we solve all of these problems? Well, that's again what reactive programming is trying to provide here. So what is really reactive programming one more time? Well, think of it as data flow and composition of events. If you want to think about the word data flow, well, data flow computers really were were exciting back in the 80s, or maybe even earlier than that, maybe 70s. And the Dataflow computers were a failed attempt, but the concepts were really, really exciting. And the idea behind Dataflow computers were that anytime a computational unit receives all the data that it needs, it is ready to fire its computation. And they built hardware around it where there would be computational units hanging around in these processors, and the data is ready for its execution. It'll fire and then distribute the data to other waiting computation engines. Well, machines at the hardware level didn't really help along these lines. However, the concept of data flow has been quite exciting, and people have been working on it over the past several decades now. And so this concept has not really died away. It simply is transforming and taking different shapes over time. But rather than using the word data flow, let's use a slightly different word, because that seems to ring the right bells these days. Let's use the word stream. Now, think about stream for just a little bit. If you look around, there are several things that are like a stream of data. I'll talk more about this in a few minutes, but imagine I turn on the radio station. My favorite is NPR. I listen to the National Public Radio in the US all the time, and I turn on NPR. There is a program that's happening. I can listen to this program. There's a stream that's coming through my radio or through my computer if I turn on to their website to listen to it. But there are times when I'm traveling and I cannot really get my favorite programs like Morning Edition. Well, I can always go back and listen to the stream that has been saved, and I can replay it over the day. And as a result, you can think about this as a data, but it's a stream of data that's coming in, and I can process it. In a similar way, applications can work with streams of data, but we'll talk about what those streams are a little later. But then we want to also worry about composing these set of streams of data and working through them. Well, I want to emphasize one thing. The question is, how do you really make things fast? And I've come to this realization, you don't make things fast by putting more resources into it. So I'm going to make this statement here, that efficiency is attained not by doing tasks faster, but by avoiding those tasks that shouldn't be done in the first place. So if you really want efficiency, we have to be smart not to run fast, but to slow down and say, let's figure out what we don't have to do. If you eliminate things you don't have to do, you are not using as many threads anymore in your application. And those threads can be used for serving real needs rather than serving perceived needs or obsolete needs or obsolete requests. That can be extremely efficient as well. So to make things efficient, we really want to eliminate tasks that we don't have to do rather than putting more threads into it. What is the benefit of doing it this way? The benefit of doing it this way is if you eliminate the task you have to do, you don't need as many servers and as many threads anymore as we used to in the past. So by realizing this particular request is no longer relevant, I'm going to dump this activity and I'm not going to process this anymore. Your thread readily becomes available to do some other work, and as a result, you can end up using a lot fewer threads, and in turn, you can end up using a lot fewer servers, and as a result, we can be more efficient in the elasticity, and that often has an impact on the bottom line, because the more servers that you use, the more resources you use, the more you end up actually paying as well, and who wants to end up paying a lot anymore? So you want to be very efficient for the services you get. So efficiency is something we have to think about quite a bit. But what about failure? Well, we need to really respect failures from the get-go. We have been treating failures as a second-class citizen, and guess what? That's one of the reasons why failures hurt us the most. Because the failure eventually says, you didn't care about me when you were doing work, why should I care about you now, right? So as a result, be kind to failures, respect failures, then the failures kind of are easier to handle. So what if we start dealing with failures from the beginning? Well, how do we really deal deal with failures from the beginning? Well, we haven't really figured out a good way to deal with this over time. Way back in time, we used to return error codes. Now, how did that work? Well, that really sucked, right? Because we said, if you get a positive value, this is a result. If you get a negative value, it's an error, because a result can never be negative, right? And that didn't go very well at all. Then we started throwing unions of object, and that didn't go very well. And of course, we fixed all the problem eventually because we have this fantastic idea called exception handling. So exception handling is awesome, right? Because we can say try, and we can call the method, and very quickly we have an exceptional way to handle it right away, and that solves all our problems. So that didn't go very well at all, because the pattern of programming has been suppress that exception. How many times have you seen people use empty catch blocks, right? Well, absolutely, right? So many of us raise the hand. But I never blame programmers, because programmers don't even do this, because modern IDEs vomit that code right away, right? And the programmer's like, I didn't even notice that there was an exception here, because as they're coding, something pops up. Nobody pays attention to what pops up. They hit the return, and plop, it really vomits a little bit, and right there is the catch block like that. So there goes our exception handling, right? So this didn't really take us too far at all, unfortunately, because an exception, the code is crying, and we put a tape on its mouth and said, be quiet now, I don't have time to deal with you. So exception goes wayside, and then now we have problems to deal with. I actually was working with an application not too long ago, and it was failing miserably. And I spent 2 hours trying to figure out why it is failing so bad. And after 2 hours, I could not find the answer. Desperately, I start, to go through every line of code, and I eventually come to the code where the code says, call into this code below. I go into the code below, and the code below clearly has an error message. If this is a situation, then blow up with this exception. And the minute I saw that code, I'm like, of course, I know what the problem is. And then I asked myself, why did it take 3 hours to find this? Then I go to the level above the code that is calling this code, and the code said, catch the exception and suppress it, rascals, right? So the point is, this is really hiding the details, and we don't know what's going on, and it's very expensive for us to find and fix these kinds of problems eventually. So we got to handle this with a great amount of respect and vigor. That's very, very important. Okay, that's all great, but here's something that's been happening for a while that is working in our favor. And one of that is functional programming. As I was reading about reactive programming, it really jumped out of me to say, aha, reactive programming is really a next logical step from functional programming. So it is more like a functional programming plus in my opinion. And the reason is, I see that this is a logical step from functional programming is, functional programming already has these very two fundamental concepts that are very important in reactive programming. And I talked about the data flow, and I said, let's use the word stream. Streams are a nature quite a bit in functional programming. We're dealing with the streams of data in functional programming quite a bit. We also deal with lazy evaluation also quite a bit. So think about streams for a little bit. Now, what about a stream? What does it mean to be a stream? Well, let's think about this for a second with a little example here, if you will, and then we will go back and look at some more details. Let's say for a second, I'm going to come up with a list of values to work with. But you can start looking at a problem very differently. For example, what if I want to compute a lot of prime numbers? Well, what kind of prime numbers do I want to compute? I want to compute prime numbers starting with a number, and I don't know how many numbers I want to compute. I'll tell you later. Well, how could we really build this? We could do something along these lines, right? So for example, I would say public static, let's say for a minute, I'll say Boolean, and I could write something like is prime for a minute. Let's give a number to this guy, and he's going to tell us whether a given number is prime or not. But how do I really deal with it? Well, I could say int stream, for example, dot, and I could ask him to provide a range of values from a particular number to, let's say, to the given number, here, and then I could ask him, well, now that I have a range of values, I could say none match, and I could ask to do an index given a value, number mod 2, for example, is equal to 0. So we are looking at a way to look for whether a number is even number or not. So we could say, for example, number is, let's say, greater than 1, and we could ask for this particular result over here. So if you look at this, that is going to tell us if a given number is a prime or not. We can easily write this using a stream. And so this notion that we can start beginning to think about a lot of things, a stream of data begins to show up. But what is even better is, let's say I want a list of prime numbers starting with the particular number. So I'm going to say stream.iterate. What number do I want to start with? Let's say 100, and I'm going to say E, and then E plus 1. Well, what is this called? Let's stop right here and think about it. Well, this is a stream of numbers. Well, how many numbers do we have here? It's literally infinite numbers. Now you may say, it's an infinite set of numbers. How the heck would you store? Well, that's what we have the cloud for, right? No, just kidding. So the point is, the beauty of this is combination of laziness and streams together. And the beauty is this says, I will create an infinite collection if you dare to ask me an infinite collection. That is the cleverness in this code, is that it relies on the lazy evaluation. So the block of code I've shown here, where E is going to transform to E plus 1, this code is the lazy evaluation part. That is never going to get evaluated unless you really ask for a specific value. In fact, it is on demand, and that is an example of lazy evaluation. We don't do any work unless we really have to do that work, and that becomes a lazy evaluation. So now I can simply say here, well, filter for me, given a value, only filter values that are, let's say, the prime numbers, and then once you do, I want you to only get me a limit of, let's say, 10 values, and then once you do, I want to print each of these values. So we could say system.out print line, for example, here, and we can print out these values. So if you look at an example like this one, that is prime numbers from 100, but we only got about 10 different values. So you can, hopefully this is a very simple example to understand the two concepts together, the infinite collection, a stream of data, and the lazy evaluation mixed together, right? So if we can start thinking along these lines where we can take a stream of data coming in, but we do lazy evaluation of the data along the way and start processing it, then we got the benefit that we can work with. And I believe actually that reactive programming kind of starts right here and moves forward to build the things that we talked about, because we can mix streams and laziness very effectively to get our work done. So that is one of the biggest benefits we see of these kinds of approaches. And with languages like Java, C#, JavaScript, and almost every language worth its salt now has a functional style of programming in it. We can do some programming like this in almost every language, and so reactive programming becomes a nice logical step move forward from that particular code. So think of it as stream, and think of the laziness. Let's think of stream for a minute. So help me out here. What in your mind is a stream? Examples around you. Can you think of streams of data around you? Throw a few things at me. What was that you threw at me?
Data.
Data. What kind of data? Any data from a database potentially. Maybe. What else? What was that?
The video stream.
The video stream, absolutely. A video stream is a stream of data. What else can we think?
Your talk.
My talk. Well, that is a very sputtered stream. Okay, what else? Music. Music could be a stream, absolutely. We listen to music. That's a stream. What else, please? Reflection. What? Okay, all right. What else? Video games. What in a shop? Orders in a shop. Yes, orders in a shop could be a stream. Inventory information could be a stream. What else can we think of? What is it? Events? What kind of events? Like conference events and stuff like that. Things that happen. Stock prices, that's another great example, right? Where the stock market keeps fluctuating and there's a stream of data coming in. What else can we think of as a stream? Weather data, absolutely. Facebook, weather data. Both of those change so rapidly. What else? Exceptions. Well, yeah, when they're not caught and suppressed, absolutely. What else? File content could be a Twitter streams. What about time? Is time itself a stream? It is, right? So what if you think of doing timers as an event on a time stream? And as the stream of time comes towards you, you start processing things. And what if mouse movement is a stream? What if mouse click is a stream? What if keyboard typing is a stream? So everything we can work with, we could start thinking about as a stream. So a stream could be a data that constantly changes and evolves. And once we start looking at our world as streams, then we pretty much can deal with almost anything reactively. Am I making sense so far? That's a stream as well, right? Your reactions coming in. So absolutely. But we can be lazy about evaluating things. Why? Because there are certain things that are not relevant. We don't have to deal with every single thing that happens. We want to only deal with things that matter, so we could be lazily evaluating things. Now, in Agile development, we use a term called last responsible moment. What is last responsible moment? It is when you no longer can avoid doing it. And there's a difference between procrastination and last responsible moment. Procrastination is, dude, you should have done this 3 weeks ago, you haven't done it yet. That's procrastination. Last responsible moment is, you cannot wait anymore to do this, but a minute or so before, you could have still waited. Now, I'll give you one example of last responsible moment or lazy evaluation. Well, I live in the US, like I mentioned earlier, which means I have to pay taxes. And honestly, I don't mind paying taxes. But the one part that I hate the most is filing my tax return, because that is such a waste of time. And so I always wait until 11 p.m. on April the 15th. At 11 p.m. on April 15th, midnight it's due. At 11 p.m., I have a conversation with God. I say, if I'm going to live for another hour, let me know. I want to do it now. Because if you're going to die before April 15th, why would you want to waste your time filing the stupid tax return anyways, right? That's the last responsible moment, right? So be lazy and postpone things and do it when you absolutely cannot delay it any further. So laziness can be very effective also. So being reactive, how do we go about doing this? Well, people say this is really an extension to the observable pattern. So reactive programming actually was coined by Eric Meyer as he worked in Microsoft a few years ago. So this has been around. He created a reactive extension in the .NET platform. And then, of course, a few years later, people looked at what he has done and they got excited and they ran with it. And now you have so many different implementations out there in various different languages and platforms. Well, when you think about reactiveness, it is an observable pattern, but if you really look at the traditional observer pattern, even Java JDK has an observer pattern implementation in it, isn't it? But what does it really do? Well, you subscribe to an observer, and the observer notifies you when there is a particular data available. Well, take this as Observable Plus, where we add a few more bells and whistles to observer. Reactive programming uses a very powerful observable. This observable sends you a stream of data. Again, look at the word Dataflow as a stream of data. You are pushing the data rather than pulling the data. Once you subscribe, you can sit there and keep receiving the data as the data flows through towards you. It can tell you when there is no more data to send towards you. There'll be a signal to say, I am done, so you can do the close-up or terminal operations and you can move on. And it is very respectful of dealing with errors. So So it's an observable where errors are not treated as second-class citizen. Errors actually are handled fairly well and packaged really nicely. That again is something that's built in this particular case. And it could be synchronous, it could be asynchronous, it could be lazy evaluation as well. So think about this as a packaging of certain solutions put together. So enough talking, finally. Let's talk about this through some code. But what kind of language am I going to use and what can I do here? Well, I'm going to use two languages here today, but you can do this in almost any language you want to use. I'm going to use Java for about 90% of the coding today. So I'm going to use Java and show you some examples in Java. Well, on the JVM in Java, or on the JVM in different languages, there are quite a number of implementations for reactive programming already. My good friends at TypeSafe have Reactive Stream available. There are a few other solutions available as well. But I'm going to use here one that is called RxJava. And RxJava is an open source tool created by Netflix. Apparently, they have some streaming issues to deal with. And so they have been working on this quite actively, and they have put out RxJava. So I'll use RxJava for most of the examples today here. But towards the very end, I also like to kind of play with other few fancy things. Always there's a toy in my toolbox to play with, and the toy that I've been playing with, I'm not using the word toy deliberately here. Anything is a toy to me when I play with it. And the toy that I've been playing with recently is really a beautiful language called Elm. And Elm is considered to be a reactive functional UI-driven tool. And I'll bet you will fall in love with Elm when I show it to you if you haven't looked at it already. So I'll show you just one little example in Elm towards the very end of this talk as well. But you can leave this room and program in any language using any library. The concepts are pretty much the same. The APIs are going to be fairly different. So are we ready to get started with some code? All right, let's do that. Well, I need a help from one person who has a smart device so they can look up stuff. Who wants to help me here? One volunteer. No, not Ted, no. Who wants to help? One person with a smart device. There you go. Please come on over here, sir. Let's ask for his help. All right. Hey, how come you guys didn't clap when I walked in here? All right, that's good, that's fair. Awesome, so let's get ready for his help. What's your name, sir?
Alex.
Alex, glad to have you here.
Thanks.
Are you ready?
Yeah.
All right, so Alex is our victim here today, and volunteer here today, and he's going to help us with this. So Alex, I want you to tell me the stock price for these three, Amazon, Google, and Oracle. Alex, are you done?
Nope.
Alex, we're waiting, Alex. Alex is way too slow. Do you think so? Absolutely. What's going on, Alex?
I'm trying to Google it.
He's trying to Google it.
And the Wi-Fi here is slow.
Why? So he's got excuses now.
Oh yeah, absolutely. I've got Amazon.
You took all this time only to come up with Amazon?
Mea culpa.
Thank you, Alex. Well, stay here. Alex nicely demonstrated the so-called worldwide weight. That's exactly how web servers work, isn't it? You're a great sport. That's what you showed us. So I make a request to the web server, and what does the web server do? Takes a collection of data and says, I'm going to go look at it. And while it's looking at it, you said, hey, here's Amazon's value to you, and you continue to do more work. We know what that technology is called. We call that Ajax, right? So you pushed a little bit of data to me, and you continue to work with it. Now, while you're doing it, I'm going to turn to them and say, never mind, Alex is really slow. What are you going to do?
Get frustrated?
Well, yeah, that's good. But you're going to continue to keep working, right? Because you don't know that I told you I don't want this anymore.
Yeah.
That's exactly how World Wide Web works today. Well, thanks for demoing that for us, Alex. Great. Appreciate it. Thank you. Excellent. Give me a hand, please. So that is an example of how the World Wide Web works, and I know that Alex will never volunteer again if I ask for help. No, you've been a great help. Thank you, Alex. So the point really is, that is kind of how we've been programming the web, is we push a bunch of data to the web server, and what does the web server do? It is my responsibility now to process all of this and keeps going at it over and over and over. And while it's doing, the client may have actually left. We could have closed the browser. What does the server do? Actively spinning, and eventually finishes and says, where did the client go, right? So the point is, that's a complete waste of time. That is not efficiency. Now, what if we can build a smartness where the server says, hey, the client is no longer interested in this data anymore. Let's just not do this work. What if you're going to Netflix and you're looking for, it's a boring afternoon, and you really have watched so many movies, so you want to know what movie you could still watch. It's a frustration, right? You look for movies, been there, seen that, don't want it, don't like it. And then you say, oh, scroll, hey, look, that looks interesting. And now you want to watch it, but you have sent a genre that you're interested in, but you don't want the server to be spinning more movies at you with an infinite scroll. You want to say, I'm done. I don't want any more information, right? So in other words, how do you communicate to a server, keep sending me data, but only until I tell you I don't want any more? So we'll talk about some of the ways we can build all of these with a little example. So how would this feel like? Let's look at one example of observing this data and implementing it. So I'm going to say here, stock server dot get feed, and I'm going to say symbols over here to ask for the symbols and get a feed for all those symbols. So all I'm doing on the client side, okay, let's talk about client and server. The word client and server is a bit misleading. So think of this as a client component potentially on the server side, because you're going to have a close interaction. If you want remoting, you can build remoting on top of these things. For example, Akka provides a fairly nice remoting along with message-driven architecture, and reactive streams in Akka would be a great candidate for that. Well, talking about that, let me quickly mention, now that we have all these different solutions out there, we got one problem already on our hand. If you build a solution with, let's say, RX Java, or somebody with Reactive Stream, somebody else with .NET extension, well, we got different solutions. But one of the other things that's growing right now is this idea of microservices. Well, what if you start building multiple microservices, but one of the true characters of microservices is you could use different languages to build multiple services. And as a result, what if one service uses one technology for reactive programming, another service uses another technology? How do you communicate back and forth between them? That could become a potential problem. Well, there is a little idea, a great idea, called Reactive Stream. And the idea behind Reactive Stream is a group of companies and people have gotten together. These are folks from organizations like Twitter, Netflix, Oracle, Microsoft, TypeSafe, and I'm sure there are other organizations that I'm not mentioning here, but they have put their heads together to come up with a standard specification so that you can write your code in different languages, but you can interoperate much more freely. They're working really hard. My personal opinion is I'm thinking they're probably about 6 months away before this is really production ready, but it's well worth paying attention to reactive streams and see what's happening in that area. So I've created a little GetFeed over here, and I'm going to go ahead and implement this GetFeed. So what am I going to do here with the GetFeed? I'm going to return an observable over here, as you can see, and observable stock info is what I want to return from here. Well, what is this observable that we have on our hand? And I'm using the RX Java's observable, as you can see right here. So as soon as I call the GetFeed, the GetFeed is returning an observable back to the caller and saying, here you go, take this observable, be happy with it. Well, what am I going to do with the observable on this side? I'm going to store that as a feed right here, and once I store it as a feed, I'm going to now say feed dot, and I'm going to subscribe to this feed. Now, what do I want to do with the data that comes in? I'm going to just be a little trivial here. I'm going to simply say system.out colon, and print ln, and all I'm going to do is just print the result that has been given to me. So I don't really care to do much processing. All I'm going to do is, as I get the stock prices, I'm going to just print it out, right? Somebody mentioned earlier that stocks are a stream of data, so absolutely we could start getting the stock price and print it. And so in this case, I'm just printing it. But I could do other things with it. Rather than printing it, I can make a decision based on the stock price and say, oh, this is the stock price. It looks like a nice price to do a trade. Or this is a nice stock price. Looks like a nice thing to keep down and note it down and do some comparison, or send it off to another server for other processing and transactions. Whatever that could be, I could do it right here. So that is my code on this side. I'm getting the feed, and then I'm going to subscribe to it. Is the font size for the code big enough for the people in the very back? Give me a thumbs up if it's good. Awesome, thank you. So that's basically what we're doing here is we're simply printing out the result. That's what we are doing. Great. Now let's go to the GetFeed method. What are we going to do with the GetFeed method? I'm going to simply say over here, observable, and I'm going to ask him to simply create a particular output for us over here. So let's say observable, so observable.create, and what am I going to create at this point? Well, I'm going to create a little service receiver on this side, but you can look at the laziness already. The code said, get me feed. We didn't do any real work. We immediately gave an observable and said, here you go. And the guy on the other side says, thanks, I've got an observable, and we didn't do any real work, right? We're postponing the work. Then with the observable, you come and call a method on it. Now we are saying, I'm going to do some work for you. So what am I going to do here on this side when you call the create method? I'm going to say subscriber, and now that I have a subscriber on my hand that I want to talk to, I'm going to say while true, and in reality, if I had the power in the world, I would have a fairly better access to the stock information, and I don't have to really do this kind of while looping, but I don't have such access, so I'm going to simply use a service to get that information and send it off. So notice what I'm going to do. I'm going to say symbols over here, dot, and we said this is kind of like a stream of data, so we'll say it's a stream, and I'm going to perform a map operation, and I'm going to say stock info, and we'll call a method called fetch. Let's quickly understand what the stock info really is. Well, the stock info is more or less a POJO. It contains a ticker symbol and a value as final public fields, a constructor that initializes those two fields, fetch method, which is a static method, we'll come back to that in a second, a toString method that prints the details. In the fetch information itself, ignore the commented out code for a minute, but the return new stock info and the price, the ticker symbol, and I go to Yahoo Finance, get the price of the stock, parse it, and then false simply says, go get the real data, don't mark it up. I'll mark it in a few minutes when I want to do a little bit more with it, but for now I'm going to get the real data. If you look at Yahoo Finance, it simply is parsing the data from the web service, so there's not a whole lot to look at it really, and that is basically the code I have in this particular case. So once I get the stock information, what's the next thing I'm going to do? Well, I'm going to say for each of those, we have a stock info on our hand, and I'm going to say subscriber, and I'm going to send it to the subscriber. So I'm going to say subscriber on next. And so I'm pushing the data using the on next. If this is a bit clearer, look at it like this. This is really getting the stock info. So I'll write it in both ways now. Stock info, and then I'm going to say subscriber.on next, and I'm going to send the stock info to it. So all that I'm doing on the side is I'm sitting there getting a stock price, and as soon as the stock price is available, I'm pushing it to the subscriber using the special method called the onNext method. So there's a shorter form of using this, so I'm going to remove that part and put a method reference so I can remove this verbosity in the code, and that's all I have done so far. So once I do this, I'm going to just delay this a little bit, so I'll call sleep 1,000, so we'll just give a little bit of a break so that it doesn't run crazy, and then I'm going to basically, in this case, say implement the sleep method, and the sleep method is going to be simply, I'm going to say ms for a millisecond, and I will say thread.sleep, and let's call this as as whatever millisecond it is. And of course, it wants us to handle the exception, but we are all experts in handling this kind of exception, so that's taken care. So that's basically called the sleep method to work through it, right? So we can implement that method very easily and provide that kind of service. So that takes care of looping through and getting the values for us. Well, that's great so far, but I just realized, being reactive here, I don't have the password. Does anybody have the password for the...
Box 14.
All right, cool. That was easy. Let's see if that works.
All lowercase.
Awesome, thank you. So let's see if that works, actually. So let's go back and fire this up. So back here, let me make sure that it actually is connected. So let's fire up the browser and take a look at it real quick. Yeah, seems like it. Okay, so let's go back and run this real quick and see what it has to tell us. I don't need these streams over here. All right, sounds good. So fire it up and let's see what it has to tell us. Well, right there, Alex, is that correct price? So that's pulling the data and it's displaying it, as we can see. Not a whole lot of code in this particular case, but that's the live data that we are pulling in as we are running this code. So what did we do so far? We subscribed to a service and said, I've got an observable I'm going to receive the response from, and as soon as you receive the response, I want to do something with it. You could send this to another method and do processing, send it across, store it in a database, what have you, but you're processing essentially. But if you look at this particular model, what we are doing is we subscribe to a service, and then we sit back and we keep getting the stream of data, and as the stream of data is coming through, we are doing some processing with it. So that is what we did so far. Looks this reasonable so far? Right? So it's purely an observable that we have implemented at this point. But there is one other thing you can actually do, and just to illustrate that, let's say I'm not going to do this forever. Let's say I'm going to do it just once, just for this example. Let's say we're going to do it just once. And then when I'm done with it, what am I going to do? Well, I want to tell the client I don't have any more data. Well, you can communicate that to the client by saying subscriber.onCompleted. So this is a way for you to signal to the client, I don't have anything more for you. You can do your wrap-up operation. So this can be useful in where you have a live stream, but you could signal that the stream is over and there is nothing more to process, so the client knows there's no reason to wait longer for more data. Nothing is going to come through, so you can send on completed. Now, of course, the question is, how are we going to handle this on-completed on this side? Well, you can see that the 3 data came through, but how does the client know that there's no more data? That would be nice to have that information. Well, we're going to scale up a little bit to handle that real quick, and I'm going to say over here, new subscriber, and I'm going to say over here, done, for example. So if I go back and run this code this time, well, let's go ahead and output this information right here. So I'm going to output, let's say, the stock info. And if I run it this time, now you have a way for the client to be known that there is no more data coming. You can see done being displayed right here. So that shows that there's no more data coming through. So you can implement a little bit more detailed interface to get that information. You can handle that. So I'm going to scale back to the code we had a second ago, so I can illustrate yet another point. We'll come back to that in just a second. So once again, I'm going to go back to the code we had a minute ago. Now we have a stream that's going to go for quite a while. So let's stick with that for a second and see how this is going to go through. So now we have this code running through, and we are able to see that a stream of data coming in, and this is actually scrolling through. You're not able to see the scrolling, but because the data is kind of almost the same, but hopefully you can see the scrolling up here right in the bottom. You can see it flicker. So that is more data coming through as we are working with it. That's great so far. But there is one other problem I want to talk about before we take a break, and that problem is, well, that's great. Now we are able to get the observable. However, What if the client has subscribed to a stream of data and the client is really looking for some specific data? Like, for example, I would like to trade if a stock price is below a certain value. And the minute the stock price is below a certain value, I don't want any more stream. I want to go off and do trading, and I don't care about the stream anymore. Well, it is rather impolite to just walk away, because I want to say, server, thanks for your help, but I don't want this information anymore. I want to go back and do some other work, and so you better release your resources. It would be nice to communicate that back to the client, isn't it? So, to the service, isn't it? So notice what I'm going to do here. This is going to be a little example just to find a way to send this information back to the service. So let's say for a minute, I'm going to output right here. So let's go ahead and say in here, output stock info. Well, now that I've printed this, just as a hypothetical example, let's say if, let's say math.random is greater than 0.95, this could be, rather than being a random, usually this will be, oh, I'm looking for this particular stock price, and if you hit the stock price, I'm done. I cannot really put a stock price here because I don't have control over the stock market, and as a result, I'm just put a random number for myself here, right? So what am I going to do at this point? I'm going to simply say unsubscribe to say, thank you, but I'm done. I'm going to move on to something else. You don't have to send me any data anymore. And let's also go ahead and say over here, output, let's say that's it. Thank you, right? So we're going to just print that out. So let's go ahead and fire this up. And as I'm running through this code, you can see the data coming through as this goes on. And it says, that's it, thank you very much. You saw that message, right? So it said, thank you very much, no need for the data anymore. And it said that, and you can see that up here, right here, somewhere along the lines. There we go. So you can see that, oh, there you go. It says, thank you very much. But do you realize what's happening? Looks like this guy is begging now. Thank you, please be quiet. What's going on? Well, our service is like some employees at work that you know very well. You go to them and you ask for a help, and they start answering, and you get it right away. You say, thanks, I got it, and they don't stop, right? It's like, I really got it, thank you. No, let me explain really well to you. It's like, you want to leave the building, right? The service is kind of like that. It doesn't get a clue, right? So it doesn't want to stop, and it keeps on going at this point. So what do? Well, let's fix the service to take care of this properly. So I go back to the service and I say, hey, service, just don't keep going like that. Poor client tells you really when it is no longer needed. So subscribe dot is unsubscribed. So this is a way for you to say, only keep working when the client is interested or the service listener is interested. So this gives you a back and forth communication. You are requesting the service to send you a stream. The service starts sending you a stream. When there is no more data, it can tell you there's no more data, but you can also tell the service, hey, thanks, but I don't need this anymore. You can stop sending me the data, and so the service now can relinquish the resource and go do something more important. Remember what I mentioned about efficiency earlier? It is knowing when you don't have to do something so you can do more useful things. So when the client is no longer interested in the data, this is a way for you to free up your resources, if you will, and so you don't have to waste your time and effort processing. And once you get the signal that you don't need to do this anymore, you can then terminate right away. So there's a bit of a delay here, obviously. You would expect that in the case of, the processing, but you can see that in this case it said, yep, thank you, and the service is no longer sending the data to the client because the client said, thanks, but I don't need the data anymore. So this gives you an idea about how you can unsubscribe from the service as well. So what is the benefit of this unsubscription? The unsubscription benefit is you can host a lot of different clients, but the service can become more efficient. And when a service no longer needs a service, there's a nice way for the client to say, and the server now doesn't have to really use a lot of resources to scale. This can minimize the amount of memory that you are using on the servers. This can reduce the amount of threads you are using. This can reduce the number of servers, machines you have to use. So all these collective benefits can come your way. Please.
The flag that is shared between the
shared memory, and it may be a contention?
Right. So that's a really good question. The question is, hey, there could be a flag and it could be a contention between those two values. That's a really good question. Let's reflect back on message passing that we talked about a minute ago. So some rules we have to follow in message passing. And number one rule is when we are dealing with messages that we are sending, the messages absolutely have to be immutable. That is one rule number one. And thankfully, notice that what I have done here is that in this case, I have made a stock info as purely immutable. So there is no change we can make to a stock info once we create it. And so that is our responsibility as application writers. We should never pass anything that's mutable. As an extra tip here, most likely this has to be serializable as well if you're going to go across machines, because otherwise you'll get a serialization error. But having said that, hey, what about the communication between in the language, in the not the language, in the framework or the library itself? That's the good news. Those guys know what they're doing, right? So when we call the methods, they take care of synchronization and concurrency and all of that. This is already done within, for example, things like Akka, because that is their main effort, is they take care of these synchronization primitives. So anytime you call a method and if you have to go across threads, they take care of synchronization for you. They make sure that they don't run into race conditions, so all of that is taken care. We shouldn't put any shared memory ourselves. We should only go through this library to communicate. So we don't want to create a global state and say, you go talk to this from here and you go talk to this from here. You shouldn't do this. As long as you're sending an immutable object across these services, you're perfectly fine, and you don't have to worry about the rest of the things. They take care of it under the hood. But absolutely a concern we need to definitely keep in mind. We cannot totally ignore that. Yep, please.
But does it mean that once the subscriber unsubscribes, the server keeps still a reference, so it's not going to be garbage collected?
For the client, you are saying.
Yeah, when the client unsubscribes,
Right.
the server looks like it keeps still a reference.
Right. So the reference is pretty lazy at this point, and the reference you're going to keep at this point is going to be, so you're going to bail out of this. So you could write the code to get out of the subscription. In that case, this would be the only object hanging around. But when the client goes away from the feed, for example, if the client no longer wants the feed and if the client goes away from the feed, then that can be garbage collected. So that's a question of saying, hey, I'm a client, I don't need this information anymore, I'm going to leave, and then of course garbage collection will happen at that time. But the memory internally used will go away because you are out of that method that you were. You no longer have to stay in there because the processing is over. So think of, that's rather more important, because this is a very thin lambda, right? Not a whole lot of memory is used for it, but connections that you have open, memory you've allocated internally, other resources you are engaging, that's where the real expense is. You can get rid of all of that because and give it to another client. That way you can make a better use of that. That's where the real saving is, not in the little lambda. That will go away eventually, but that's not something to worry about. That's very thin memory anyways. So what did we do so far? We talked about the concept of reactive programming. We talked about how to create this observable. Then we talked about making a request and coming back. We're going to take a break, and when we come back from the break, let me quickly show you what we're going to do. We're going to talk about error handling, and then once we talk about error handling, we're going to talk about a little bit of how the client can control what it actually sees in terms of selecting some data. We'll talk about asynchrony after that, and then we'll talk about very slow clients. How do we deal with back pressure? And then I will talk about a little bit of reactive Elm. So when we come back, it's going to be almost 100% coding, except for maybe about a 5 or 10 minute talk in the end, whereas in this part we did mostly talking and a little bit of coding. So that's what we're going to do. 30-minute break, and when we come back, we'll look into the rest of the aspects. Thank you. All right, welcome back. Let's talk about a few more things. We talked about making a request, getting some data, subscribing to an observable, and then we talked about potentially unsubscribing from a feed. Let's talk about failures just a little bit. Well, Murphy said if something can go wrong, it will, and failure is the reality. And what if things actually fail? There are 2 or 3 different ways to think about this. Let's talk about what's going to happen when something actually goes wrong. Well, in a multi-threaded application, when a single thread fails, the first challenge is how do we propagate that information all the way to the other threads? Well, if you're running in an executive service or a thread pool, often the thread pool catches your exception, and of course, it just throws it away, or logs it, or finds other ways to propagate it to you. But the real challenge is what happens when many things go wrong exactly at the same time. Well, there are certain things we should do about it. Well, let's talk about what's going to happen when there is an error. Well, in order to simulate this, what I'm going to do here is let's fall back on just outputting the value first of all. So let's say system out, and I'm going to simply call a print line over here and just get the result out. And in this case, I don't really care about terminating the service when I no longer want the client to do, because the client is not communicating that, but that's okay, we don't have to worry about it. Let's go back and run this little code and see how it feels. Well, in this particular case, obviously, we're going to keep getting a stream of data, and the client is not terminating. So that's great. The code is back to where it was a little bit ago. But let's say we are going to have some kind of an issue on the server side, meaning at some random time, well, in reality, something could actually go wrong. And when something goes wrong, you want to notify that there's a problem, you cannot continue. What kind of problems could happen? It could be a logical error. We could run into some kind of a computational error. It could be a data that is not really a valid data. It could be data corruption. It could be a network error. It could be a database error. I mean, the number of reasons why things could go wrong is very countless. So if something can fail, it can fail in so many different ways. So in this particular example, when something did go wrong, I'm throwing an exception. In this case, oops, ran into trouble. Well, what I'm going to do on the server side now is I'm going to say, put a little try block, and we will say in this case, catch, and let's go ahead and catch the exception that happens. And when an exception happens, what do? Well, what have we done so far? We've tried a few different solutions so far, right? We said, here is a result for you, and if the result is actually an error, we'll pass the error with it, and good luck on dealing with it. Well, that's one way to handle that, and that didn't go very well. Then we came up with exceptions. And the point about exception is when something goes wrong, we'll blow up from the current stack, and that propagates down to the caller. If the caller doesn't handle it, goes to the caller's caller, and eventually, if nobody handles it, it blows up the application. Well, in theory, that sounds like a great idea, but in practice, we often find people handling the exceptions improperly, mostly out of frustration that when the compiler forces them to handle it. I mean, this has been a pattern, right? The Java compiler especially has checked exceptions. Whether checked exception is a good idea or a bad idea is really not a debate anymore. Because if you look at so many languages on the JVM, most languages do not have checked exception. Only Java actually forces that on us. So in the case of Java, when you write the code, what does Java say? The Java says, you will handle the exception. And the programmer says, let me show who's in power here, and puts an empty catch block, right? So there is no way to win this battle, right? You never mess with programmers. The language compiler should know that. But if you treat the programmers with respect and say, here's an exception, I hope you are smart enough to handle this, then the programmers raise up to the challenge and say, let me see what I can do about it. So that didn't go very well at all, and we failed miserably in exception handling. But also comes the question, do you really want to blow up the stack when something really happens? And we could argue maybe a good amount of exceptions really are not exceptions at all. They should really be errors that get propagated and not exceptional situations. So in order to handle all of these, well, we could do something along these lines. We saw on completed before, we saw on next also, right above, we are using on line 14, but this time we're going to say on error, and we're going to propagate the error. So in other words, when an exception happens, or an error happens more so, it doesn't have to be an exception, you're going to send the details of the exception. So you could literally create an exception object, but you're not throwing an exception. Instead, you're just handing over the exception and saying, here you go, this is information packed with the details of what went wrong, deal with it. Now you can also have nested exception details in this as well, so you can pass that exception over and say, here you go, deal with it, do something that you would like to do. But if I go back to this code, notice I've not really dealt with the exception at this point, and when I run this code, notice that it blew up right now, and look at the error message. It says, on error, not implemented exception. So it says, how dare you did not handle the error properly. So in other words, it clearly communicates to us that we have not taken care of handling errors. Remember, treating errors as first-class citizen, treat errors with respect, use them along the way, and that way you have recognized that something could go wrong, and when it goes wrong, you're ready to handle it. So what can we do about it? Well, think about this as two different channels coming at you. There is a data channel and there is an error channel. The data channel is giving you the data as the stream of data is coming towards you, but when something goes wrong, an error channel is going to give you the error through it. So in other words, notice in this particular example, on the service side, we simply said, if something went wrong, I'm going to send you an error. That's all we did. So if I go back to this code right here and run this, you can see it failed because we didn't handle the exception. So what I'm going to do is simply say, in this case, system and out, let's call print line one more time. In this case, all I'm saying is, I just want to print the error. So you can see those two channels in front of you now. So you have subscribed two channels. Here is the data channel subscription, and here's the error channel subscription. So it's pretty clear to see what you're dealing with here. And of course, you don't have to print these values. Instead, you could have just sent these values to another function to deal with also. Now notice something interesting that we observed over here. When there was data coming through, we got the data through the data channel. When something went wrong, we got the error through the error channel and not through the data channel. What is the benefit? The first benefit is we're not doing silly if-else conditions. We're not saying, if this is a good data, deal with it. If this is an error, deal with it. We're not doing that if-else condition. There's a clear separation of the functions to receive it. We're not dealing with exception handling like we do exception handling. So we're not blowing up the stack and stuff like that in this layer. We are gently handing over the failure and saying, here something went wrong, deal with it. But there is something else that you can see here, you probably noticed. Remember, I was in a while loop going through, and when there was an error, I simply called on error, and the service immediately said, I'm sorry, something went wrong. I'm going to stop doing my work. Now, think about this for a minute. When you're in a web situation, when you're talking to a service, you run into some kind of a situation. Maybe the situation is you got a network error, or a database error, or a security error, whatever that you run into. What is the most logical thing to do when that happens? The logical thing to do is to report an error and not really make things worse by continuously pinging. But what do services normally do? Oh, there's an error. Retry, retry, retry. That is called desperation, right? And there's no need to be desperate like that. Instead, raise the error and say, I'm going to try this after a while when I know that things could have recovered fairly well. Well, what if you don't do that? What if you keep retrying over and over? Well, typically this is like a pileup of cars where the cars are driving too close to each other on freeways, and one hits the brake and there is a slew of 2 miles of traffic, crashing into each other, and systems become like that. So one trigger facilitates a cascade of failures, and the problem becomes so intense, it becomes really hard to recover from that and restart. So you don't want to pile up things like that. So the default behavior, as you can see here, is that it simply stops the minute it runs into a problem. Now, is this a good idea? Well, it certainly is a good idea when that's, for most of the time, I would argue. So you run into an issue, you're notified about the issue, and you go figure out what the problem is, and then you can restart the service. You decide that based on what your needs are. But there are times when you run into an issue, but you want to switch over to another service when you run into an issue like this. It reminds me of one experience I had. I was working for a company where they wanted us to build an application where we would gather up some information from the user, and we have to do quite a bit of processing, but we needed some critical information that we had to obtain from a third-party web service. So we would make a request to the third-party web service. The third-party web service will give us the result, and when it gives the result to us, we will continue with our processing and return the response to the user. Well, in their infinite wisdom, the company found one third-party service that was absolutely cheap. And you know where this is going? Well, it was absolutely cheap, but when I started integrating with the service, and during testing time I found out the service was really cheap, but it would fail multiple times in an hour. So how do you deal with a service that fails so many times? So we're struggling with it, and we found a service that was somewhat expensive, but boy was it reliable. Its mean time of failure was really small, into milliseconds in several months, whereas this other one will fail multiple times in an hour. So we were trying to debate with the company, and the company finally said, no, we definitely want to use the cheap service because we want to save the money. So my job was wonderful in this particular project. My job was to talk to this cheap service, and if it worked, do the processing and return the response to the user. If it fails, quietly switch over just for that one request to this expensive service, get the result and process and return the response to the user, but the next request from the user will try the cheap service again. It was really not a very fun job to do, because you're doing this for the reasons of using the service which is cheap, but nevertheless it seems to work really well. So there are times when you want to do the switch over potentially and use a different service as a fallback. You could do that. Well, this is really built as more of a chain of responsibility. So in other words, think about it this way. Here is a service, and the service may work properly most of the time, but the minute the service fails, it immediately stops sending you any more stream of data. That's the default behavior. And if you use the service directly, that's what you get. But instead what you can do is, you can attach it with another service. Maybe you want to think about this as a proxy or an intermediary, if you will, and you are making requests to the intermediary or the proxy right now, which in turn sends a request to the real service. The real service makes a response, sends it back to the service, and this one will immediately send it back to you. But the minute the service fails and disappears, this intermediary says, oh wait, something went wrong, let me notify you of the problem, but I can, on your instruction, maybe restart another service, maybe to another server if that makes sense, and can do a switch over for you. So for example, let's quickly take a look at an example of that. If I run this example one more time, you can see that in this case, the data starts coming in, and at any time it runs into an issue, it immediately stops on hitting that issue, as we can see in this particular example. Well, what I'm going to do instead of that is, I'm going to not directly subscribe to the service, but I'm going to simply say, on error, resume next, and then I'm going to subscribe to the service after that. So you can see the pipelining or the chaining that I'm going through right here. So in this case, we said, on error, just start off a next one, and this is going to receive a throwable, again, as an object over here. So throwable, and what do I do with this throwable? Well, I'm going to first of all say output, and let's just say, oops, the first service, so the first service failed, and then I'm going to say here output the throwable that we got, but then I'm going to return, and this could be to any service you want to go to, but in this case I'm going to simply say over here, let's call it as stock server dot, GetFeed on the symbols, and I'm returning a new service. But again, in reality, you could configure a third-party service, a different service, whatever that you would want to do, you can switch over like this, as the case may be, and you can do whatever that may make sense, depending on what your real situation is. So the idea really is, if I run this code now, what is it going to do? Well, notice in this case, we are running with the first service. The first service failed. You can see the oops, the first service failed error message right there, but you can see at this point it started continuing now with the second service. Well, sorry, the second service also eventually failed, and this is called bad karma. It eventually catches up with us. But the point is that you can switch over and try to recover and get a little bit breather out of it. So you can again start configuring this to a various degree and extent. You can configure it in a way that you can propagate a state and say, can you please start with this now, and then you can switch over. So there are quite a few interesting things you can do depending on what your intention is. But notice how this is nicely chainable. Somebody who subscribes directly with the feed is going to receive a terminate on the first failure. On the other hand, somebody who subscribes with an on error resume next has the ability to continue further when such a failure happens, and then can roll over to another service. So you can treat something like this along the way. So that is one of the examples that you saw here as to how we can deal with errors. So to summarize that part, we are dealing with a separate channel for error from the channel for data, and when an error happens, there's a termination of the stream automatically. But of course, you have various different configurations to say, when an error happens, I want to resume next and move on, and I want to provide an alternate service, or I want to take some corrective measure and then switch over to a service, whatever that may be. You can try to figure out what those solutions are, so it gives you an opportunity to respond to it. Well, that's great so far. However, let's think of another scenario. If you think of a process industry where maybe there are refineries that are working at a very high degree of temperature and pressure, and control systems often are keeping a close eye on several unit operations in a refinery. Likewise, you may be monitoring a particular flight data, and flight data is a stream, as an example, right? So while a flight is in transit, the flight's altitude, the temperature, the pressure, the fuel level, where it is at the moment, various other things, who is at the deck, all of those things are going to be data about a flight, and you might be monitoring that flight information. Likewise, in the case of a process refinery, a stream is the temperature and pressure of various units that may be coming in. Now, maybe what I'm interested in is I am interested in monitoring a particular unit, whatever that unit is, but I'm interested in monitoring it maybe at a certain point in time. And maybe in the case of a process unit, maybe there's a startup time when I don't care to monitor it. Don't bother me until it reaches a state of stability. Or don't bother me until it has hit a threshold. And the minute a threshold trips, an alarm goes off, I want to start monitoring. So in other words, you don't want to be given a stream of data all the time. You might want to define a window when you want to receive a stream of data. So to understand that and how we could potentially do this, let's get rid of the error message for a minute. Let's go back to this particular solution, and all I'm going to do is simply display here just the details about the data itself, so we can quickly take a look at this, and we can see in this particular case we're going to just keep getting the data as the time goes on, and we're going to be seeing the data as you see up here. But what I'm going to do is change that just a little bit, and I'm going to say, well, I am not interested in all the data right now, so I want to perform a skip operation. Earlier I was talking about functional style of programming, and I was mentioning in functional programming we deal with streams and we deal with laziness. Well, one other operation we deal with in functional programming is these operations like skip and take, which are very powerful operations. Because if you remember, in the first example I wrote, where I was trying to compute prime, and I was told during the break that it was not actually prime at all, that it was actually looking for even numbers. Hey, that's great. That's the solution I created. And the point really is, but we still said limit this to 100 values, and I don't care about any values after that. Well, absolutely, we said limit, and that is an example of having an infinite stream, but looking at a window through the infinite stream. This concepts really come from this ability to really look at a stream and look at a segment in the stream. So I can say skip, and I'm going to ask it to skip 10 values and then start over. So if I run this code, you can see there's a bit of a silence in the beginning, and then after the 10 values are over, you can see this is starting now. So that is an example of skipping based on a duration. So you can say skip for 10 values. Rather than doing that, you could also say 10 over here, so another form of skip. So you can say skip, but rather than saying a number, you could say skip, let's say 10 comma time unit, well, not days, whatever that value could be, right? So you could skip for a little duration of time and say skip for that time and then start doing stuff. Let's just say 1 second here for us, let's say 2 seconds. So I'm going to run this now, and it's going to wait for the 2 seconds. This could be like a warm-up time before it starts sending you data, and you can see that happen as well. So you can see this chain of responsibility coming through. Or what you can do is, you can also do skip while, but before I come to skip while, let me go back and make this a true, because I want to mock up some data rather than using the real data from the market. Then I can specify some details about the price easily. So skip while, I'm going to say stock info, and in this case, while the stock info dot value is less than 1900, let's say. Now, this is nothing but, most of us would look at this and say, if you're worked with functional style of programming, you would say that's a filter operation. Well, yes, it is a filter, except this filter is going to block the data from moving forward until that particular filter predicate is tripped. And the minute you trip the filter, the gate opens up and the data goes through. So visualize this as a stream with a block, a door being closed, and this condition will trip the door, and now the data will start flowing through. And that kind of visualization can be nice to have, that you have a stream that's being blocked, and then you are essentially implementing a trip for that particular circuit breaker, if you will, for that particular gate. And once the gate trips, your data starts flowing through. So if I run this code this time, you can see that it's silence again, and I don't know how long I'm going to wait, because until a price becomes more than 1900, and you can see that the price is more than 1900, I'm sure people in that company would be loving to have these kinds of stock prices, but not yet. So that's an example of how you can see the skip can be implemented. So the idea behind skip, and we saw 3 different forms of skip here at least, and the essential idea about skip is you can skip for a certain duration, and for a number of count, like a warm-up time. You can skip for a duration if it makes sense to skip for a duration, or you can skip for a particular condition to be met as well, and you can decide what option that may make sense. So you can do certainly a skip operation. Much like that, what if I did a skip operation, let's say skip while, and then I said stock info, and when the stock price goes to that value, what is going to happen now? Well, when I run this, of course, it's waiting for the stock price to go up to that point, but the minute the stock price exceeds that value, the gate trips, and then, of course, the data stream comes in, and this is going to go until it runs into an error, or the service says, I don't have any more data, and stops. Well, which is perfectly fine. But think of another scenario where you are monitoring a particular unit, and the unit has reached a threshold. Or I'm monitoring a stock, and the stock has hit a price that's favorable, and what do I want to do? Now I'm interested, but I'm not interested for a very long time. I might say, well, the minute it trips, I am very eager, but I want to only take 10 values from that time onwards. You don't have to use a skip to use a take, but in this case, I'm skipping some values, but then I only take 10 values after that, and you can see it stopped after that because we hit that limit of 10 values. So you can start writing code in a way that you can define this window. When do I want to start? Do I want to start on a time, on a condition, on a count? And when do I want to stop? Do I want to stop on a count? In this case, we stopped on a count. You can also stop on something like 2 dot, let's say 2 comma time unit, and then you could specify, let's say for seconds, for instance. So in this case, I'm saying when it trips, I want to be notified, but I want to only be bothered by this for about 2 seconds. I'm not sure why that actually bailed out right away. So that's going to say that I want to be notified for only 2 seconds at this point. You could also specify take while, for example, where you can say stock info, and you can then say the stock value is, let's say, greater than, let's go ahead and say, 1500, for example, right? So you can say the minute that trips, stop sending me data afterwards, and you can then say, I want to only listen when that condition is met, and the minute that condition is met, I want to close the gate. So think of a take as, skip as opening the gate, and take as closing the gate, right? So you can have these kinds of boundaries set up to do things based on what you're trying to do. And that can be very effective in specifying a window that you want to look into. So that is an example of how you can write, process the stream, but we saw a few already configurations. One of the things I like about this is this nice chain of responsibility. And you can think of some really good design principles, right? One of the nice design principles here is the separation of concern. And the separation of concern is the service only focuses on notifying things. It could be any service, whatever, doesn't matter, and the on error assume next, and the skip and the take are all little proxies you add on top of it. So this gives a nice extensibility to what you're trying to do, rather than polluting a code with all these different details. So really nice design in terms of good software design principles you can see shining right here. Well, the next thing I want to talk about is how we have been running this so far. So to understand how we have been running this so far, let me take this out of this for a second, and let's just go ahead and subscribe this service like we have right now. But I'm going to go ahead and call another method here. So let's go ahead and say, in this case, what I want to call is sample. Let's go ahead and call it as process over here. So I'll say process, and I'm going to call a method called process. Now, what is this method called process that I'm writing? So I'm going to say, here is my method, and the method I'm interested in writing, let's go ahead and say static void process, and this is going to take a stock info as a parameter that's being passed into this particular method. So now that we have this method on our hand, what I want to do with this guy is I want to say, let's just print out the information. Let's do that first. Then plus, I'm also going to print out the current thread information also. Well, we have been doing this sequential up to this point. So if I run this, you would notice that this is all in the main thread at this point. So that shows to us we are actually single threaded, which is perfectly fine if, remember, I mentioned that this is not really a client. This is really a client-side proxy on the server side, because you're interacting closely with the service. And you can configure based on different needs. However, this could also be remote if it makes sense, depending on what you're trying to do. But the idea really here is you are saying, well, my client is going to take a little bit longer to respond. What are the things you could be doing? Notice I've just written the output here to the terminal, but I could be doing other things. I could be writing to a database. I could be sending this off to a remote service. I could be doing some extensive calculations with it. I might be grouping some data, and then when bit of a data is available, I could do some processing. The possibilities are endless in terms of what you may do with the data. It depends on your application. It depends on your domain that you're working with. There is no way to control this. But there's one rule we have to follow in reactive programming, and that is a client should never delay the service, and the service should never force the client to be any faster than it really is. So these are two rules, right? The rule number one, a client should never delay the service. If the client says, call me and I'll take my sweet time to do my processing, then the service is going to be delayed by it. You don't want to do that. So you don't want to block the service because the client is slow. At the same time, you don't want the service to say, hey, client, speed up, come on, let's go. You got to be faster than you are. You don't want the service to force the client to be faster than anything it is. So how do we manage this? So in order to do this, there are certain options available for us. Well, the first option here is you could go for an asynchronous client. Now, how do we come up with an asynchronous client? Well, the needs of a client is very different. There are certain clients that would rather have a new thread to run things on. There could be a certain client that might have a new I/O operation it performs. Maybe it opens up a socket, maybe it opens up a file. Now, let's understand one small detail when it comes to the number of threads that we can entertain. If, let's say, your process is computation intensive. So if it's computation intensive, what does that mean? You are going to be running like crazy performing computations, and your code is busy doing this computation. Well, if your code is busy doing work, the last thing you want to do is interrupt that core and say, hey core, I know you're busy, but take a break and switch over to this computation you can perform. Well, that's not going to be saving any time actually when the core is very busy number crunching. It's going to take a break only to number crunch more. In that case, this is all within a process I'm saying, and in that case, what's going to happen? You're going to actually trash by switching threads when you could have actually done more work staying with that thread. So in other words, how many threads should I have if I'm very computation intensive? It doesn't make sense to have a lot of threads when you have computation intensive tasks, because the more threads you create computationally intensive, you're going to challenge the core to do context switching. That's not going to be really good in performance. Actually, on a computation intensive problem, the more threads you create, you lose performance actually. On the other hand, if my task is I/O intensive, well, what does that mean? If my task is I/O intensive, that means I'm going to make an I/O call, and while I'm blocked on the I/O call, I'm not going to do anything much at all in this thread. Well, you can throw a lot of threads on this particular problem, because when a thread is blocked on the I/O, it can might as well, the CPU, core might as well switch over to work on another task, and so you can entertain a lot more threads when your task is I/O intensive. So there are these kinds of decisions you may have to make depending on what your problem is, and you may want to say what your intentions are. So the idea really is when you have these kinds of differences, you want to communicate that really well. So to do this, what you do is, rather than calling the subscribe, what you do is you call subscribe on, and you are asking it to do a subscription, but now you are coloring this or annotating it or flavoring it or mentioning, whatever you want to call it. You are saying, I would like to ask for a bit of control over the threading at this point. So what do I want to say in this case? I'm going to say schedulers, so we could say schedulers. And what am I asking for? We could say new thread, for example. And then I could simply say over here, for each, go ahead and print that result on that particular schedule. So if you notice over here in this case, of course, sorry, we put it on a separate thread, obviously, in this case. So I got to wait for this guy to finish. So I'm going to simply say, in this case, let's say thread.sleep. Let's give it a little bit of time and see how this runs through while we are waiting. Well, in reality, you would put a more control over knowing when to quit and stuff like that. So you can see that it's putting it on a separate thread at this point. Well, the tasks were relatively quick, so you can see that it's actually reusing that particular thread. But the point really is that we delegated to a separate thread. It's no longer the main, as you can see in this case. So by flavoring this, again, you can see this nice chain of command that you see here. As it flows through, you tapped into the chain and said, hey, I don't want to be handled right here. I want you to switch over to another thread and handle it. So now the service is firing the data at you as a stream, but you are processing it in a separate thread, and you could do whatever that may make sense in this other thread. Of course, if you have concurrency problems, you got to manage it. Somebody was asking earlier about concurrency. Well, on your side, you are still responsible for concurrency if that matters to you. But of course, on your side, what you can do is if concurrency becomes an issue, you can use messaging on your own side and throw it on a message queue rather than processing it yourself, so you can avoid the synchronize and suffer problems that we normally get into. So that gives us an idea about how to use maybe a new thread. We could do that. Or what we can do in this case is, rather than using a new thread, we could say it is an I/O operation, and we can simply say this is going to be a I/O, and so that is just a different flavor that you are asking at this point. And this is simply managing based on the threading, so it can use things like fork join API and make a better utilization of the thread depending on which thread is blocked and which thread is not blocked and stuff like that. Or what you can do is you can say from, and you can use the from to specify what thread you want to run into. This gives you a little bit more control, if you will. For example, what I'm going to do here is I'm going to say executors, let's say, and I'm going to create a new fixed thread pool, let's say a pool of 100 threads right here, and I'm going to save this into an executor service. And let's say at this point I'm going to shut down the executor service. We could also say await termination, all those good stuff. Certainly we can do that, but in this case I'm going to simply specify the executor service up here. So now you can see it's coming from the pool of thread, and because it's coming from a pool of thread, you can see that it's going to reuse our pool of these 100 threads we have provided. This is going to use from that pool of threads, so you can control which pool of threads to provide as well for this asynchronous work. So what does this do in this case? It says, you know what, I've got stuff to do, but I want to do this in an asynchronous thread, and so as a result, as you fire the data at me in the stream, I will branch off and do the processing in another thread. You can do that fairly easily, as you can see in this particular example. Well, that's great, but what if my client is extremely slow client? What should I do in that case? So to understand that, I'm going to say thread.sleep here, and let's really delay it and make it rather fairly slow. So in this case, you can use asynchrony, no doubt about it. However, rather than using asynchrony, let's try out a slightly different option. This is often talked about as back pressure. So what is a back pressure? A back pressure is where the data is coming at a really great speed, but the client simply is not ready to handle the data at that speed. Now, this is a communication you have to go back and forth between your service and the client, but the point really is you are telling the service, you know what, I cannot handle at the speed in which you are generating. Could you please start buffering the data and then start sending it to me at the rate in which I am ready to handle it? Now, this is all purely contractual. You can decide what kind of back pressure you want to apply. One example of a back pressure is, I'm going to give you a current data that's available, right? So in other words, I have a lot of data being generated, but if you want the data, I'll give you what is right now, but if you are done with it, and then you come back and ask for me more, I'll give you whatever the data is right now. I am not going to buffer them and give it to you. That's one option. Another option is, I'm going to buffer up all the data, and as the data is, you are making a request, I'm going to keep giving you a data. Now, it really depends on application you are dealing with. For example, let's say I'm dealing with an application that is monitoring, let's say, a vehicle. So you got somebody on the street and you are interested in their current position. Well, the current position is coming to you and you're handling it. Well, now, a few seconds later, you're caught up with your process. Maybe there was a delay in processing on your side. You most likely don't care about all the position they took. You are very interested in their current position as they are right now. And so you don't care about a back pressure of all the data, but you want the data at this very instant in time. That could be one example. But there are other situations where you do really want all the data as they have been processed and received. So it really depends on your domain and your application. Well, how do we control some of those things? Well, in order to control, you still have to decide how much of data you're going to buffer. All of those concerns are still there. But in terms of the communication, you could do what is called a producer and a consumer situation. So to understand what this means, let's look at one example here. So what I'm going to do is, I got a slow process absolutely sitting here, but here's what I'm going to do with the slow process. I'm going to first of all go back over here, and I'm going to say, well, here's the feed. So feed dot, and I'm going to subscribe to this feed. And when I subscribe to this feed, I'm going to say subscriber, and I'm going to implement this interface as you saw here, and implement this new subscriber. But on next, I'm going to simply call the method that we have on our hand, which is process, and I'm going to give him the stock info. However, my service is going to be rather slow in processing. So what am I going to do? I go back to this particular code and I implement on start. And in on start, I'm going to say request, and I'm going to say, let's say 1 for a minute. So this simply says, hey, I am ready to process, but I'm going to make a special request to you so you can send me one data that is available, right? So in this case, you're making a request for as many data as you are comfortable handling. Maybe you can handle 10, maybe you can handle 100, whatever that could be, you can make a request to that much amount of data. And the service now can send you that much amount of data and sit back and relax until you go back and ask for more data at that time. So to understand how this is going to work, let's go back to the service right here. And what I'm going to do in the stock service is, rather than implementing it this way, let's get rid of that for a second. And I'm going to simply say, now that you got the subscriber, I'm going to say subscriber.setProducer. And so we are implementing a producer of the data. When a request is made, that's when the producer kicks in and produces the data, and then sends the data back, and then you can go back and do more work. Now what I can do in the producer is, I can say, given a request that you have received, so let's say request, and what do I want to do with the request? Well, in this case, whatever is the number of requests that you have created for me, so I could say, for instance, for, well, let's say in this case, we could use a for loop if you are interested, or we could change it to a stream, but I'm going to say for int I equal to 0, well, let's actually say long I equal to 0, I less than request. And in this case, I'm going to say I++. And what is my, well, actually it's complaining. Let's fix that for a second. So because we are writing, implementing a lambda here, let's go ahead and put this as for, let's say long I. This is going to be equals to 0, I less than the value of request itself. And let's say I++. And what am I going to do at this point? Well, I'm going to say symbols.stream, and let's get the map as we did before. So we'll do a map and say this is going to be stock info. So this is stock info.feed. And once we got the value on our hand, let's go ahead and say for each, I'm going to go ahead and say subscriber. So here's my subscriber, and on next. So we are pushing the data on next each time as and when this particular request can happen, right? So subscriber, let's see why it's complaining. So subscriber dot on next, and that's where I want to push the data over to the service. as and when it's happening. So let's fix that. So that is an example of how much you can send. In this case, as many requests you made, I'm going to send that many batches of data over to you. Well, let's see if this works. So what I'm going to do in this case is I'm going to go back to the client, and I'm going to run this side of the code, and you can see in this case it produced that value over here, and that's a slow processing nevertheless. We could put it in asynchrony, but it only gave us one data, as you can see. Why? Because that's what we did. We said, I request you to send me one data. But what you can do is you can then say, hey, thanks for sending this over to me. Now I want to request one more time as many data as you would like to request. So in this case, if I want to run this one more time, you can see that the data came over. We are processing the data, and you can mix this with asynchrony as well. And then once I finish this, oh, that's funny. It's only sending that Amazon, so we got to see what the problem there is. But you can see that in this case, it's going to then start sending one data at a time and process it. Let's go back here and change this to 3 values, because we said 1, and so he's literally doing it 1. So let's say 3, and then go back and run this one more time and see how many on next is going to process for us. So in this case, you can see, well, let me go fix the code. So let's see what I made, where I made a mistake. So we are making a request at this point and saying, give me the data. Let's go to the stock server, and we have the 0 to whatever that request is, and here's the stream, and I have asked it for the stock info, and for each one of them, I'm sending the value over here on the request. So I'm not sure exactly why that was not giving us the result. Anybody sees the error here? What is it? Right, I'm requesting a new price to send. That's perfectly okay, because I want to send a batch of requests, right?
When you receive 3 at the first one, you request a new one.
That's right. And when you send it, because this is a map and this is a for each,
It's about the timers, because it's just 1 second and 2 seconds, and every time it's the first of the new set.
right. So the timer, but we are sequential in this point though. So yes, the timer is slowing things down, but nevertheless, that shouldn't be causing the other data not to be displayed for us. So I'm not exactly sure. I got to debug this and see what the problem is. So the idea really is that we got to send the request, and only as you make a request do you get more data. So if I don't make any new request or decide I don't want any more requests, then you're not going to get back any more data from the service. So you can see in this particular case that it is giving us the 3 data. Oh, I know the reason for that. You're right. Because when the data starts coming for one at a time, you are absolutely right. Thank you. So, that's great to hear that debugging. I love paired programming, as you can see here, right? So we got to keep a count of some sort and say, have I received 3 response back? If I received 3 response back, then I want to go back and make a request. So you probably have to handle that with a bit of a counter in this case. But nevertheless, I want to extend this to something a little different, if you will. So let's think about this for a second. Now, in this example, at least the way the RX Java is implemented, it makes a request, and the request is the number of values you are receiving. So clearly what I would have to do in this case is, I have to do something like this. I have to say, if the count is minus is equal to 0, then make a request, right? So I got to keep a count of the number of response I'm receiving. You have to do it this way. But I want to entertain a slightly different thought here. What if, rather than using the length, what if we change it just a little bit? Now, this is not the intention. The library has not been written with this intention, but I'm just tempted to hijack that library and do something a little different just to entertain the thought. And I'm hoping really that they would provide this mechanism eventually, because I believe this can give us some really interesting flavor. So let me explain to you what I mean by that. So I'm going to put a 0 here over for this as a value 0. I'm going to print stock info. Then I'm going to say index. Now, clearly I'm violating the API, right? The API is not intended to do what I'm doing here, but entering this thought. This is relatively new. Who knows? Before this is fully baked, we may have a function like that, and I'm really hoping we would. So pushing the boundary just a little bit, just a thought, my own eagerness here, what I would like to do is simply say int index equals, and in this case, I'm going to say index plus 1, and I'm going to modulo that with stock info dot get, And what am I interested in? Symbols.get. So symbols.get, and I'm going to get in this case, or rather the index of, well, actually, sorry, size. So size. So what am I doing in this case? I'm saying I want to take an index value, but what is index? Well, initially, the value of index, let me actually move this up here. So the value of index is going to be symbols dot index of stock info dot, let's say, ticker. So in other words, you have sent me a stock info, I process that, but as soon as I process the stock information, I want to know what stock I processed, get its index, and then make a request for the next stock information, right? So as I said, I'm completely hijacking this API from being a number of requests to giving a little context of what I want next. Then I go back to the service, and notice what I would like to do here in the producer. Rather than doing all of this stuff, what I'm going to do is I'm going to say int index is going to be long, and I'm going to convert this request over here, and then I'm going to say, over here, let's get the value, the feed itself. So subscriber dot on next over here, and what am I going to send to this guy? Stock info dot fetch. Well, I'm going to fetch from the symbols. I'm going to get the value at that particular index. So essentially what I'm doing in this case is I'm asking it to get me that specific value. So clearly, I've not done what was intended from the API, but I'll come and explain to you what my desire here is. So in this example, you can see we finished Amazon, asked for Google. We finished Google, we asked for Oracle. We finished Oracle, we went back to Amazon. We are round-robining through it. Of course, if you had more data, you'd keep going on to the next one. So in other words, what I am trying to do here is something that we all have talked about in the past, but we rarely did within Java, which is this beautiful concept, one of my favorite concepts called continuations. So continuations really is an ability for two endpoints to really have a contextual state going back and forth, right? So you go to a service. If you really look at a traditional web application, what happens? You make a request, you go through a process, send a response, and the next time you go over there, knock, knock, hey there, hey, have you met before? And we start establishing the context one more time, right? That is basically how the web normally works, and that's kind of like, I call this like the programming like Dory in Finding Nemo. Remember Dory? Every few minutes, hey, how are you doing? Good to see you again. That's kind of the way web servers work, right? Every time you got to reintroduce yourself. But what if continuations can be there, where you can do some work, leave to the client, do some work, and come back right where you left and continue with more processing? That would be really awesome. So maybe I'm crazy, I'm thinking it wrong, but that's my desire. If we can have like a continuation where you can push a state back from the client to the server, and the server can then hold the state and get back to you, I think that would be kind of awesome in my opinion. So I don't see why APIs cannot extend to saying, hey, you decide what that state is, because it's purely like a memento pattern, right? You capture a state, send it to the client can take the state, send it back to the server, maybe something like that can happen. So anyway, just a little thought about maybe we could try something along those lines. So what I did was I talked about some of the features here and how we can apply some of these concepts. I want to switch gears now and show another example where we can do something along these lines. But essentially, I want to kind of revisit, talk about a few things, and then come back to this example in just a few minutes. So to reiterate what we talked about, the idea behind reactive programming is to really honor scalability, resilience, responsiveness. These are very core expectations. And we are able to do scalability using the concepts of message-driven architecture, elasticity for scalability, resilience, really honor errors with respect, and responsiveness as well. Well, what is the benefit of being message driven? We are not fighting the battle of concurrency. We are delegating it to a higher level of abstraction. As a result, we don't have to sit and fight these problems and say, now I have conquered this concurrency problem. Instead, you can focus on solving the application and domain problem rather than beating around the concurrency issue. Now, Now, as a result, your application can respond really nicely without really being bogged down by concurrency issues. And what's good about it? Well, your customers are going to get a better throughput in your application. And when throughput is better in your application, that's going to help retain better customers as well, better users as well. So that's one big benefit. Elasticity can be a huge time saving because we can scale into multiple processors. As far as elasticity is concerned, I was mentioning that efficiency really comes from not doing work faster, but by really avoiding work that shouldn't be done in the first place. So if we can figure out a way not to really do stuff that is not necessary to do, we can be smart enough to delegate those important resources for clients that really require processing from us. What is the benefit of resilience? The resilience is the easiest way to make sure applications suck less. So as a result, it doesn't fail inappropriately. It handles things very gracefully. That can be very, very powerful. And of course, responsiveness is a way to retain customers as well, because they come to the application and the application is providing valuable information rather quickly. Especially with devices today, we live in this world of instant gratification, so we cannot simply punch and then wait for a long time to spin. We got to start moving forward. In fact, in a way, I would argue the devices really have changed the world, because we don't have a luxury of polluting huge amount of information on a screen, because the screen size is rather limited, and as a result, we really give this bite size of information to the user and make it very usable. I'll give you an example. I won't mention the site name here. I use a site very often, and they have a desktop application and they have a mobile application as well. And even though I'm sitting in my office in front of my laptop, I often pull out my phone and I use their mobile application, only because they don't throw things at me that I don't care to see. This mobile application gives me focus, and I just get the work done and I move on. When I go to their web application, they want to throw all kinds of garbage at me. I'm like, I don't care about all the stuff you have, and why should I get distracted? More effort to use. So mobile applications tend to do that already. This can be in favor of that to really push what is more important. Now, having said all of that, I'm going to give you one example here of something else that I've been playing with, and I'm rather pretty excited about it. This is a language called Elm, and how many of us program in JavaScript here? Quite a few. Keep your hand up if you love JavaScript. Oh boy, really? Okay, well, JavaScript needs a little bit more love. We can all agree to it. But what if you can write JavaScript without even realizing you're writing JavaScript? That's been the trend lately, right? I mean, name the languages that transform over to JavaScript. Well, Elm actually is pretty interesting. Elm syntax is really Haskell syntax, but it's a Haskell that gets compiled down to JavaScript. This is really beautiful as long as you don't open the JavaScript and look at it, right? So don't bother looking at the JavaScript it generates unless you are willing to have an ambulance waiting outside. But the point is, it is really beautiful when you look at it. But this is called as a reactive language for reactive UI, a functional reactive UI development language. Well, that's a bit of a loaded word, but what does it really mean? Well, let's look at one example here, if you will. I'm going to lower the font size just a little bit here. Is that font size still big enough for people in the back row? I see thumbs up. Excellent, thank you. So let's say I've got a main as text Elm reactive UI. I just wrote this to say that this is actually working. But let's try something else here. Now, what Elm says is, what does it mean it's reactive? Elm says, well, we can consider everything as a stream. In Elm, time is a stream, for example. Elm also considers the window, the mouse position as being reactive. So, for example, you could do something along these lines. You could say something like import, and then I'm going to import mouse, for example, here, and they have a method called lift. Now, the word lift is actually pretty interesting in my opinion, because what they're saying is, here's a stream of data coming, you lift the stream and feed a function with the lift. In other words, think think of this as, here is a function that receives the data, and you lift the stream and keep feeding the data into this function, right? So in other words, you're pipelining it. That's what you're really doing. So I'm going to say as text over here, that's a function I used a minute ago, and I'm going to say mouse.position. So in other words, what you're saying here is, I want to start streaming the mouse position as this function is working. So this essentially, mouse.position is just a stream. And you are saying, I'm going to take the stream of data as the mouse is being moved, and I'm going to keep feeding this method called asText with the data from the stream. So you can imagine the higher level of abstraction. Isn't that what we do for a living? We write code, but to comprehend complexity, we build higher levels of abstraction. Well, in the case of object-oriented programming, objects are our abstraction. In the case of functional programming, functions are abstraction. What if streams are abstraction and the reactive nature is the level of abstraction? Well, that's what you're seeing here is a higher level of abstraction where you're saying, I got a stream coming in and you do the tying of the stream into this function and start pushing the data over. So as a result, you can see that's kind of pushing the data. Let's try one more thing just for the sake of fun here. So I'm going to say here, import, let's say, window. So I brought in the window API so I can start using some of the things. Not yet, I'm not there yet. But I'm going to create a ball. And the ball I'm going to create is going to be filled. And I'm going to ask it to fill with a color blue. And this is going to be a circle of size 30 that I want to fill. So circle, and I'm going to say 30. That is an example of just a ball that I want to draw. Well, I want to draw the ball, so I'm going to say draw ball. So, but if you're curious about this, as I'm writing this code, this is Haskell syntax, but this is really JavaScript. And I will not show you JavaScript here, because I don't want to see the JavaScript here anyways. But if you really are curious, you can actually compile this using the Elm compiler, and then you can stare at the JavaScript on your own local machine. But do have some nearby help before you do it. So the point really is that it's actually JavaScript that you're really looking at. So what I'm going to do here is call a collage, and the collage is going to simply say, in this case, well, what do I want to print? Well, I want to give a width over here, let's say 100 and 100, and I'm going to say I want to draw the ball, but you can see the reactiveness right here and the composition aspect of it. So I'm going to say move to, let's say 0, 0 over here. Now, the guy who wrote Elm, he said he really liked the F# syntax, so he took that little thing from F#, so that's really an F# syntax that's showing up here in this particular case. So now I'm going to simply say over here, let's call draw ball for a minute, right? So I'm going to call the draw ball method, and right there is a little ball that I drew, right? A circle essentially. So you can easily draw this, and I put it at 0, 0, but the 0, 0 is centered against this window location you provided. So I could say, for example, let's say 200 and 200, and you can see that kind of move around based on the locations you are providing. Well, that's great, but I really want the window location. What do I do? So I'm going to replace this with the width over here and a height over here, and where I'm going to say, I'm going to take a width and height as a tuple, if you will. And so there's a tuple coming in with a width and a height that I want to work with. But where is this coming from? Well, that's going to be a lift, as we talked about a few minutes ago. Not a list, a lift. And I'm going to lift from window, let's say window dot dimensions, right? So I'm going to lift based on the current location, the dimension of the window itself that I want to work with. And I'm going to just start feeding that onwards. Let's make sure that I actually spelled it correctly. Spelling and typing correctly is still required. So HEIGHT. There we go. All right. So basically the idea behind this is you are simply asking it to draw, and you can see that little ball is based on the window that I have in here. You can see that sitting. So I'm going to just move this a little bit to get that entire window into our picture. So that's an example of how you can have this moving. But I've not tied it to another source of event yet, a stream rather, but we'll do that in just a second. So now that I have that, what's the next thing I want to do? Well, I would like to give it a position, if you will, where I can display this. So I'm going to say position that I'm going to take as a parameter coming in. And what am I going to do with the position? Well, I could use the position certainly. So notice I'm going to say mouse dot position. Well, here comes a little bit of a problem. Now we are not dealing with a stream, we're dealing with two streams. Now why are we dealing with the two stream? Because window position could be changing as well, and the mouse position could be changing also. So what do you do with that? Well, it's no longer a lift, it is lifted to, meaning I want to combine two things together to put the streams together and combine it. So this is like your zip in functional programming, right? So you're taking two streams and zipping them together and pushing this. Again, you can think of, the point I'm making here is, look at the higher level of abstraction you're programming with now. You're no longer programming with, here is a stream, here's the data, I want to work with it. You have raised yourself to saying, here's a stream coming in, here's a function, you do the routing for me. I don't want to be sitting and playing with the low level of abstraction. So now that we did this, I want to use the position. How do I do that? Well, I'm going to first of all take the position and work with it. So in this case, I'm going to say let and in. Let's say in this case, I have a x equals, let's say to float, because there's a type conversion needed in this case, and I'm going to take the position, well, first position, because position contains an x and a y coordinate, and so as a result, FST is a Haskell command for getting the first element from a two-tuple, so I'm going to say that is x. Well, when I do that now, notice that I'm moving the mouse, and it is moving, but it's a little shy, it's farther away from where I am. We can easily fix that. So I'm going to say, well, let's compensate for the window, so minus 2 float, and this is going to be the width, and width divided by 2, let's say, and now we are asking him to go exactly where my mouse is. That's a little bit better, but what about the y-axis? Well, we can fix that too fairly easily, so we can say y is going to be, let's say, 2 float. This is going to be the second position. Again, that's a tuple that we are dealing with. And then I'm going to say this is going to be my y coordinate. And then you can see as a result of that, well, okay, not quite, but almost there. Well, we got to compensate again for the height. So we can say in this case, this is going to be a minus 2 float. And in this case, let's say this is going to be the height divided by 2, assuming I typed the height properly in this particular command. So this is going to be a 2 float of the height that I want to take the value, and then once I get the value of the height, I want to compensate for that particular value in this expression. So let's finish that operation here. So that's going to be the computation for the height itself. So given that, oh, wait a minute, what did I make a mistake here? So height misspelled everywhere. Is there a course where I can learn spelling height? Okay, so let's fix it. So that's height. There's a reason why I'm short, you know that, right? Because I can't spell height. So let's fix that. So right there is height, and one more height. Is there more places where I misspell height? Okay, so right there is the little ball that moves with my mouse. Thank you. Is there a clap to say this guy can actually type eventually? Okay. Well, so the point really is that you are really looking at a higher level of abstraction to bind in the streams of data that's coming in. And I'm really getting excited about this kind of model of programming where you are focusing more on, you can try writing this in JavaScript, for example, right? So it's sure, ignore the syntax here if you're not familiar with the Haskell, but the real essence is you are taking two streams, zipping those two streams with lift2, and then feeding that constantly into the draw ball function, and you're not sitting there and dealing with the lower level of abstraction and writing this on the higher level of abstraction and letting the language do these things for you. So we are looking at a really bright future in terms of how we can start programming at these levels of abstraction, and it's a very exciting time to be programming in that, in my opinion. As you can see, this is something that is relatively new, but the concepts are old, but packaging of them is relatively new, and we are learning a great deal. And the reason for that is we are no longer programming like the way our fathers used to program, or my children are no longer programming like the way I used to program. And so this is a whole new generation of technologies and programmers, and definitely a very exciting time to be in. So I hope that you would actually be very proactive about being reactive. Thank you very much.